One more example from section 7.3. It's one that I should have probably included with the video for 7.3, but nonetheless, here's this. We talked about the properties of exponential growth in an earlier lecture or video, and we said that for something to grow exponentially, it needs to grow at a rate proportional to itself, and that the differential equation would look like this: dy over dx would equal to some constant times y. Um, we also demonstrated in an earlier video why an exponential equation satisfies this differential equation, but we didn't actually solve the differential equation with our technique of separable differential equation. So I want to go through that so you can see how that works. We're going to assume the initial condition is some value of y naught. We're just going to assume that y naught is a positive number, which, if we're talking about populations, makes sense. Just in general, this is going to make sense in the context that we want to do this problem. I hope you would pause the video and solve it yourself first, and then check your work against mine, or at least get it started so that you understand where would get stuck and where you would need some help. All right, so we got to separate the variables using some legitimate algebra. So I'm going to write the y over here using some division. 1 over y dy, that's going to be equal to k times dx. Now, since k is just a constant, it could be either hooked up with the y, and you could make 1 over ky dy if you wanted, instead of the k dx like I did. The antiderivative of 1 over ky might require a substitution if you leave the k as a factor of the integrand, but you can also factor it out. So a couple different ways of handling it. Just be careful if you move it with the y. There could be some errors that crop up, but again, it could go either place because it is just a constant. All right, so now for our integral step. So we get this equation here. The antiderivative of 1 over y with respect to y is going to be the natural log of the absolute value of y. Antiderivative of k dx, k with respect to x is going to be k times x. And of course, don't forget your constant of integration. Now, we're going to use this initial condition that y of 0 we're going to call y naught is a positive number. We're going to use that to solve for c now, like I have shown you in other examples, and as I prefer to do, as opposed to solving for it later. It can be solved for later, but this is just my preferred way. It tends to lead to less algebraic mistakes, or fewer algebraic mistakes for my students. All right, k times 0, of course, is 0, so this is just going to tell me that c is the natural log of the absolute value of y naught, or just the natural log of y naught, because we already said that y naught was greater than 0, and so the absolute value of a number greater than 0 is just itself. All right, so plugging this back in, we get the natural log of the absolute value of y equal to kx plus the natural log of y naught. Now, solving for y, we're going to exponentiate, raising both e to the power of both sides to undo this natural log over here. That's going to leave us with that absolute value of y. E is going to be equal to e to the power of k times x plus the natural log of y naught. Now remember, as we showed in other examples as well, we can separate the exponential here with the sum in the exponent into a product that looks like this. And then the e and the natural log here are going to cancel, and we're going to be left with e to the kx times y naught. So we have our absolute value of y is equal to y naught times e to the kx. And so y is going to be plus or minus y naught times e to the kx. And as you can see, it's an exponential. If you go back to the slope field examples that we did, where we had, I'm trying to remember now, I think it was dy over dx is equal to 2y or something like that. It doesn't really matter. When we did the slope field, y equals 0 was a trivial example, or solution, I should say. Anything above that was an increasing concave up curve, and anything below that, starting with a value that was negative, was a decreasing concave down curve. That's where the plus or minus here comes into play. The plus is when the initial condition is starting above the horizontal axis, and the minus is for when it's starting below the horizontal axis. or the point that the curve has to go through is above or below. But you can see when we have that form, dx is equal to k times y, we do end up with an exponential function all the way down here. So that's why that represents exponential growth. And if you see somebody referencing something is growing exponentially and they haven't demonstrated for you that it's growing at a rate proportional to itself, you should be skeptical about it. Now, if they're a scientist or an engineer, they should have enough mathematical background to understand that this is what that means. But a lot of people use it euphemistically to represent just really fast growth. But other things grow really quickly as well. Polynomials grow really quickly, not as fast as exponentials, but still. The point is, most people don't use it literally. They use it just as a euphemism for really quick growth. But as math people, we need to be more precise than that. All right. Hopefully that was helpful. Go